All right, section 12.2. We're getting close. All right. So section 12.2 is going to be all about what are called iterated intervals. Now, if you watch my 12.1 video, the idea of finding the area, the volume rather, under a surface, right? And we talked about that was the limit as the number of divisions goes to infinity, right? Of both of these double sums, where n goes from 1 to infinity, right? Well, that's the idea. Right. The idea that you're going to add them all up of some f of x, y, dx, or delta x, delta y. And so we covered that. But what does that really mean? Well, it means these guys are going from A to B and C to D or whatever. Some f of x and y. And typically what we say, well, typically we don't put these on initially. We just do this. And then we go dA. And what is our dA? Well, our dA is our delta area, which is dx by dy. And as one might understand here, multiplication is commutative. So we can write this as either dx dy or dy dx. There's a formula, there's a theorem for that. Just go ahead and throw that out, I guess. There is a theorem that describes that. You can change them around any order you want to. 1 year I thought it'd be funny. 1 year I thought it'd be funny to be able to talk about that, to be able to kind of switch the orders of integration around, and I made these kids. It was so funny. Looking back, I was kind of a horrible person to do it, but I thought it'd be funny at the time. I thought it'd be a good idea. Hey, you can switch those. You can switch those limits of integration around. You can switch the dx and the dy and then move it all around. And wouldn't that be fun? And so on. And the answer is no. It's not a lot of fun. It was pretty funny. It was kind of funny to me at the time. But then I started making the answer key, and then I saw everyone was doing poorly on it, and then I realized that really wasn't that fun. So not a lot of fun. It is what it is, though. Just be aware of that. So when we do these guys, again, we talked about the Riemann sum business in 12.1 and how it all works. So 12.2 really comes down to, this is not hard. And the guy I forgot to mention, the guy's name was Fubini. He's the one that realized that, hey, you can do dx or dy. Now, how would you do it? Well, so what we're going to be working on today is this. Here's the x and y plane. We're going to be integrating over some region from A to B in the x plane, in the x direction, and from some region from C to D in the y plane. Okay, so we're going to be finding the volume under some surface that sits above this rectangle, in other words. Okay, that's what we're fooling with today. Now, in 12.3 and 4 and beyond here, they get a little uglier because we're going to be not integrating over just a rectangle. We might be integrating over, this triangle or some such. Okay, but for right now, it's really easy. It's just integrating over this rectangle. So it really comes down to, and this is a nice, easy, gosh, I feel great. I feel awesome about myself today, Jay. Well, you should. You're a superstar, friend. All right. I don't know. Sure, let's do that. Why not? All right, +5. Awesome. And of course, I did this one on purpose because I did it such that this one has, all, there's no restriction on my domain. So I'm going to go 0 to 5, 2 to 3. Now, when it's written in this order, that's always x by y. That's just the way they give it to us. Okay? So we're doing it over this region. So you're like, oh, cool. I want to do dx, dy, Jay. Oh, knock yourself out, friend. Does it matter? Oh, no. Fubini said it does matter a bit. Okay. Now, could I do this one by hand? Yeah, I probably can. So let's do it by hand, shall we? Let's do, what is the antiderivative of this guy by hand? Well, it'd be x squared. It'd be 2x squared over 2, or just x squared. And then the y squared just tags along for fun. Let's see if I can do this. Let's see if I can make this happen. It's going to be negative cosine of x, y. And then that's a chain rule. I got to use a little u substitution. I think it's going to be over y, I believe. We'll double check myself. I'm not feeling real confident, but fairly confident. From 0 to 5. Now, when I'm done, I'm going to, whatever that integral is, I'm going to integrate that sucker from 2 to 3 with respect to y. So notice that on the top end, we plug in a 5, we're going to get 25y squared. We're going to get minus the cosine of 5y over y plus 25. I don't know if I can do this middle one by hand, but I'll try it. So it's going to be 25y cubed over 3 plus 25y. Nope. Nope. That one's killing me. I'm not going to fool with that one. All right. What I am going to do is I'm just going to go ahead and I'm going to do it one step at a time. I'm just going to confirm my integral is correct on the first one. I'm not, you hate to do something stupid and then people are like, I can't even freaking integrate, for gosh sakes. It's embarrassing. And you're like, voila. Was I correct? Oh, I see the problem is, you moron. You put a times in there instead of a plus. Gosh, look at me go. I'm in fuego. Nice, nice. So I'm just going to go ahead and throw it in there. I'm going to go comma, 0, comma, 5, see if I'm still right. Hot dang. I feel like I'm right. Am I right? Ooh, no, I missed the 1 over y. Do you see? I missed that plus 1 over y business. You see that? And why is that? Because Mr. Groom sometimes forgets. He sometimes forgets that the cosine of 0 is 1. All right, plus 1 over y. There you go. Cool. Now, we're going to integrate this sucker dy. Oh, yeah, that was actually right. Leave that alone. All right, now, okay, I'm going to integrate that guy. Now, you're like, couldn't I have nested this? You can, but I'm going to do it in 2 steps just for fun here. So I'm going to integrate this thing with respect to y from 2 to 3. And you're going to get this mess, 183.64. Okay, awesome. Now, would it have mattered if I'd integrated the other direction? And the answer, of course, is no. Let's go find out. So the original function was here. And I'm going to integrate that guy with respect to y first. Now note, this first integral looks different than my first integral from the last one, which is unsurprising to me at all. It shouldn't be surprising to you because you're doing them in a different order. If you've ever done a project around the house, or maybe at work, and someone comes in and goes, they come in and say something to the effect of, how do I want to say it? They come in and say something to the effect of, what are you doing? Like, this looks like crap. And you're like, literally, I'm in the middle of this job. Why don't you come back when I'm done, and then we'll have a chat? If you've ever had that happen before, you should understand what's going on here. Midway through, you get this mess, and you're like, well, what is that? Doesn't look like anything. Yeah, hold your horses, pal. We'll get in there, I promise. So go grab that guy. Now let's integrate him with respect to x from 0 to 5. And as Fubini said, 183.64. Come on, Betsy, you can do it. You can do it. Oh, shoot. Oh, 183.64. Yay. Now, again, I'm going to allow you to use the calculator to do the integrals. Okay. I'm going to do another easy one here. This is a fairly straightforward one. This one I can do by hand if I wanted to. And the reason I want to do this one by hand is because, well, as I say, it's not very difficult. And I just want to kind of have you guys visualize what's happening here. So again, if we integrate over okay. So you can integrate either way you like. Makes no difference to me. I honestly don't care. Let's do dy dx. dy dx just rolls off the tongue a little easier, I think. You do you. Whoops. But you do you. dy dx. So 1 to 4, 1 to 3. Nice. So with respect to y, it's going to be 2xy to the 4 over 4 plus, again, pay no attention to the 6x. What's the integral of 1 over y? It's ln of y plus 2y. Nice. And then, of course, we're going to take and do dx after we get done with that foolishness. So is that 1 to 3? Yes, sir. All right. Let's plug in a 4. It's going to be 16 divided by 4 is 4 times 2 is 8. All right, you plug in a 4, you're going to get 6x ln of 4, whatever that is. Don't worry about it. It's just a constant. Plus 8 minus, now let's plug in the 1s. You're going to get x over 4. No, x over 2, you clown. X over 2. And then you plug in the 1. Well, the ln of 1 is 0, so that's hot. So the middle piece goes away, and then plus 2. And then dx, and then 1 to 3. Now, I'm weird. I like to put all my stuff together. Call me strange if you want to. I don't care. Let's distribute this negative through. So then that's going to be, this is 16 halves minus 1 half is 15 halves x. Or 7.5 if that makes you happier. 8 minus 2 is 6. And then we're going to have 6x ln of 4. Again, whatever that amounts to. Okay? Dx 1 to 3. So let's do this. All right. Well, when you do this, you're going to get 15 fourths x squared plus, again, ignore the ln of 4. It's just a constant. So it's going to be 6 ln of 4. That's great. X squared over 2 plus 6x. That's it. And then from 1 to 3. And you're like, Jay, aren't these both x squared? They are. They are exactly x squared. So couldn't I, Jay, do this? 15 fourths plus, this is really just a 3 here, I guess, if you will. 3 ln of 4. Couldn't I just factor that out and multiply that by back that up. Can I just multiply that by x squared? That's right. That's right. So I'm just going to write it like this for a second, if you don't mind. Okay. So what I'm going to do is I'm going to have 15 fourths plus 3 ln of 4, whatever that is. Again, doesn't matter. And I don't really need the absolute values because I don't really need the absolute values because they're both positive. So let's go ahead and plug them in. I'm going to get 9 minus 1 is 8 on the top end. And then I'm going to have 18 minus 6 is 12. Should be 20. So whatever that number is, that should be my final answer. Let's find out what that comes down to be in here. No. No, 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 no. Careful, Jay. Careful, you ding-dong. That. Times only the x squared, right? So be careful. Gotta be careful. Pay attention to what you're doing. Sometimes you get a little too crazy, Jay. I'm talking to myself here. We'll see if Betsy agrees with me. And if she does, that'll just make my day. 75. Cool. Let's go see if the computer agrees with me. Again, doing it by hand versus the calculator. Now, again, I know how to do some of this stuff. And, of course, if I sat here all day, sometimes you could do like, oh, that would be a great one for integration by parts. Wouldn't that be fun? No, the answer is no. It's not fun. I always think it's humorous. People who didn't live in the old days talk about how romantic it was. Or wouldn't that be so fun to do that? No, I grew up on a farm. We did a lot of that junk. That old junk, and yeah, it wasn't all it was cracked up to be. And I didn't have to do any of the hard work like my grandpa did and stuff. So again, this is why I say one should probably not take my advice and necessarily do them by hand like that. So somewhere I made a little bit of a boo-boo. There you go. This is why I like calculators, friends. This is why I like them. Because it's a lot harder to screw them up. Okay? Still possible. Don't get me wrong, it's still possible. But where did I go wrong? Did I make a little error somewhere? Probably. Am I going to go back and find it? No. No, I'm not. And here's why. Here's the deal. What I'm going to be focused on in this chapter, pretty much the whole book actually, though, is applications. Applications, applications, applications. I could spend, as I've said before, you could spend an entire 3 hours doing 2 problems, and you might get one of them right start to finish, but then you might screw one of them up midway, and then good luck. Have fun with that, pal. That ought to be a lot of fun. All right, cool. Yeah, it's not much fun at all. So just be aware of that. Just really gross. Just really, really gross. Here we go. So we have a hyperbolic paraboloid. What on earth does that mean, Jay? I don't know. Let's find out. So z equals 4 plus x squared minus y squared. Above the square, okay, we're going to find the volume under this guy. Now, like, could you show us what that picture looks like? Probably. Let's go take a peek. So again, in the old 3D calc plotter. Reset. What the heck is this? Exactly. Kind of weird, huh? Kind of a weird looking thing. Nice. And we're interested in the region from, what did I say, -1 to 1? Yep. So -1 to 1. I'm just going to try to get you a better pic of this. Boom. So I want the volume underneath of this half of a potato chip thing. Okay. Now, to me that just helps to visualize it. I certainly don't need to do that. Remember, volume can be negative. That means you'd have a hole, but this stuff was all above the XY plane, so therefore we better end up with a positive when we're done here in a few minutes. So this one is easy to do by hand. This one literally is easy to do by hand, so I'm going to, well, in theory, easy to do by hand. So I'm going to go ahead and do that. And I'm going to do dy dx, and the reason I'm going to do dy first is because it's got a 0 and a 2, okay? That'll help me get rid of a bunch of junk, okay? And so I want to fool with it as much. I could save it for the last. You know, you do you. So that's going to be 4y plus x squared y minus y cubed over 3. 0 to 2. And so if you plug a 2 in, you're going to get 8 plus 2x squared minus 8 thirds, which is 24, 16 thirds, I guess, plus 2x squared. Now we're going to do a little dx action. Now let's do this. So that's going to be 16 thirds x minus 2x cubed over 3, -1 to 1. So that's going to be 16 thirds minus 2 thirds minus, and then it's going to be -16 thirds. And then this is going to be, it's already minus. We're putting in another negative, so that's going to make it a plus. If we've done it correctly, let's see what happens here. Okay. Distribute that negative, and it's going to become a positive here. And a negative here. So you're going to get 32 thirds minus 4 thirds, which is 28 thirds, which is 9 and a third. Let's see if Betsy agrees with us. Well, with me. Probably agrees with you. But probably doesn't agree with me. Who knows? So integrate. You're just nesting them. Jay, could you also do triple integrals? Yep. Could you also do quadruple integrals? Yep. So double integrals mean volume under a surface. That's correct. What do triple integrals mean? Well, I think I mentioned this before, that it means hypervolume. What does that mean? I have no idea, really. To be honest with you, I can't visualize it. I can't explain it to you. And I was going to say, no, Betsy doesn't agree with me, but Betsy agrees with me. If I was going to 22, I bet we would have agreed. And we did make a little boober there. Now, I'll tell you where my mistake is now that I think about it. I'll bet you $100 I know where my mistake is. It's down here. Let's come back and check this out. So if I had plugged in the negatives correctly, I think I dropped a negative somewhere. I think there was one extra negative. Negative and a negative, that's a positive. Well, what would have happened if this had been positive? I should have, somehow I should have added the 4/3 there. No, it's right there, you clown. It's Jay's fault. Look at it. It said plus, minus. I'm just an idiot. There you go. Those would have all been positive. This would have been like so. Like that. And this would have been negative. Then they would have all been positive. Then I would have got 36/3, which is 12. Again, reason number 8,000,000 why I like calculators. All right. That is literally all chapter 12.2 is. Okay. But Jay, could you show us triple integrals for fun? I could. Now remember, this would not be integrating over a rectangle. It'd be integrating over a box, a rectangular prism in essence. Because I feel like it. Okay, so we're doing dy first. That's going to be 3xy squared over 2 plus zxy from 0 to 1. So obviously if you plug a 0 in for y, they go away. If you plug a 1 in, you're going to get 3x over 2 plus zx. Now we're going to go dz, a little dz action. So that's going to be 3xz over 2 plus z squared x over 2 from 0 to 2. 4 over 2 is 2 times 3 is 6x. That's going to be 4x over 2 is plus 2x. Oh, that's nice. So I have 8x. Awesome. And if I integrate that with respect to x from 0 to 3, that's going to be 4x squared. Should be 36. Okay. Let's see if the computer agrees with us. And yes, you can also stack triple integrals. That won't happen until later. What I want you to see, though, is it's all the same. Okay, when it's over a nice rectangle, it's easy to see how it all works out. Or in this case, a rectangular prism. Okay, that won't always be the case. Sometimes we'll be integrating over some bizarre shapes, and that's where the hard part of this happens. And when I say hard, I don't mean hard. Sometimes it's just freaking brutal, to be honest with you. Sometimes it's not too bad. Say, have I done one right by hand yet? I don't think I have. I'm going to find my mistake. All right, found my mistake. If you plug a 2 in for z right here, that's going to be 6 divided by 2. Should have been 3x right here. Which you make this 6x. Is that the only mistake I made? I think so. Maybe. Nope, I made some other mistake somewhere else. So that's great. Good Lord. 3x plus 2x is 5x, you dope. Good criminy. That's embarrassing, Jay. Just quit teaching. Just stop. Just stop. So that's 45 divided by 2 is 45 divided by 2. 45 divided by 2 is 22.5. Is that right? Feels right to me. That's what Betsy agreed to. Yes, 45 divided by 2. Look at that. Woohoo! Can't add. That's your biggest problem, Jay. I guess in the world of things, it's not terrible. Anyway, that is section 2.2. All right. Show me your work. Show me the work. Set it up. Okay. On some of the easier ones, you should practice doing a few of them by hand, the easy ones, okay? I will probably make you do an easy, well, quote-unquote easy one on the test. Again, I won't do any triples on this one. They'll all be double integrals. You should be able to do something like this on the test by hand, okay? And I probably will require one of those, or at least where you show me all the work, okay, in gross detail. Now, the rest of them, I just want you to get practice using the calculator, okay? All right, that's enough. Enough said.